Welcome to The Explainer. Today, we're diving into a cosmic detective story that might just rewrite our understanding of, well, everything. We're talking about a mystery known as the dark flow. And it all starts with this one simple question that kind of messes with everything we thought we knew. For decades, the story has been that our universe is expanding, sure, but smoothly and uniformly in all directions. But what if it's not? What if something way out there in the black is pulling on us and on everything around us? To really get what a big deal this is, you first have to understand the fundamental rule of the universe that this observation seems to be breaking. Okay, so this rule is called the cosmological principle, and it's not just some throwaway idea, it is the absolute bedrock of modern cosmology. It basically says that if you zoom out far enough, the universe looks pretty much the same everywhere and in every direction. No weird lumps, no special spots, just a nice, even spread of stuff. Well, that neat and tidy picture started to crack when scientists found some really weird evidence. Evidence of a massive, unexplained motion. It's like a cosmic current, a river in space that's dragging hundreds of enormous galaxy clusters along for the ride. They gave it a pretty cool name, the dark flow. And let's be clear, this isn't the normal expansion of the universe we're talking about. Nope, this is something extra. An added coordinated movement on top of that expansion at a speed that, on this massive a scale, just shouldn't be there. And here's why this is such a head-scratcher. Look, we've known about local cosmic tugs for a while. We found the Great Attractor in the 80s, and then the even bigger Shapley supercluster. But we could explain those. They were caused by huge clumps of matter we could actually see. The dark flow, though, it's on a whole other level. It's so huge, so deep, that whatever's causing it, it seems to be coming from beyond the edge of our own visible universe. So you're probably wondering, how in the world do you even detect a faint, invisible river flowing across the entire cosmos? Well, it took a lead detective with a really, really clever tool. That detective was Alexander Kashlinsky. See, his team had this brilliant idea. They realized the clue wasn't in some giant structure they could see with a telescope. No. The clue was hidden in the oldest light in the universe, the faint afterglow of the Big Bang itself, what we call the cosmic microwave background, or CMB. They used this incredibly sensitive technique called the kinematic Sunyaev-Zel'dovich effect, or KSZ for short. Okay, imagine the CMB is a perfectly calm ocean. A moving galaxy cluster is like a boat speeding through it. The KSZ effect is the tiny, tiny ripple that boat makes in the water. It's a minuscule shift in temperature that gives away the boat's, or the cluster's, motion. Now, to pull that tiny ripple out of a very noisy cosmic ocean, the team used a genius statistical trick. They found hundreds of galaxy clusters, measured that super faint CMB signal at each spot, and then just stacked them all on top of each other. All the random noise, all the background chatter, it just cancels itself out. But if there was a real, shared motion, that signal would add up and become visible. And it did. But here's the real kicker. They split up their clusters into different distance ranges, or slices. Now, if the pull was coming from some massive thing inside our universe, you'd expect the flow to get weaker the farther out you look, right? But it didn't. The speed and the direction were the same everywhere. And that could only mean one thing. Whatever was doing the pulling had to be enormous, and it had to be outside the boundaries of our observable universe. An extraordinary claim like that demands extraordinary proof. And, as you can imagine, it kicked off a pretty intense, high-stakes debate in the scientific community. And this is where the plot thickens. The next-gen Planck satellite, which was way more powerful than the original WMAP telescope, went looking for the dark flow, and it found nothing. Zilch. The official Planck team said there was no significant motion. So, case closed, right? Well, not so fast. A lot of prominent scientists, like UCLA's Ned Wright, were pretty skeptical. He basically argued that the original result was a ghost in the machine. He thought their data filtering methods accidentally let some background noise from the CMB leak through, which then created the illusion of motion in one direction, a statistical fluke. But Kashlinsky's team fired right back. They took the publicly available data from the Planck satellite, ran it through their own analysis methods, and what do you know? They claimed they found the exact same dark flow signal they saw with WMAP. Their argument? The official Planck analysis was flawed, and finding the same signal in two totally different telescopes makes it way less likely to be just a simple mistake. So the debate was on. So this brings us to the most mind-bending question of all. Let's just say for a second that the flow is real. What in the universe, or maybe outside of it, could possibly be powerful enough to cause it? The potential explanations, they are pretty out there. They force us to look beyond our standard model of physics. One idea is that before the Big Bang, the universe wasn't smooth, it was lumpy. Then inflation stretched space so incredibly fast that these giant lumps got pushed way beyond our cosmic horizon. We can't see them, but we can still feel their immense gravity as a gentle, uniform tug. Then there's the even wilder idea, the multiverse, that our universe is just one bubble in a cosmic foam of other universes, and we're literally being pulled by the gravity of our neighbors.
And get this is what's so incredible. Years before Kashlinsky even announced his discovery, a physicist named Laura Mersini-Houghton used her multi-universe model to predict that we should see a bulk flow of around 700 kilometers per second. It was an almost perfect match. For her, the dark flow isn't some weird anomaly. It's the first piece of hard evidence that other universes are real.
And you know, far from going away, this mystery has only gotten deeper. The cosmic case has been completely blown wide open by some stunning new evidence from totally different investigations. And this new evidence comes with a statistical significance of 5 sigma. Now, for those of you who don't know, in physics, that is the gold standard for discovery. It means there's only a 1 in 3.5 million chance that what you're seeing is just a random fluke. It's as close to certain as you can get. So, what is this new evidence? It's something called the matter-dipole anomaly. Scientists mapped out hundreds of thousands of distant quasars all across the sky, fully expecting them to be spread out evenly. But they weren't. Instead, they found this huge imbalance, a lopsidedness in the cosmos, pointing in a direction suspiciously similar to the dark flow. This is a completely independent line of evidence that suggests the universe is not as uniform as we thought. And now, a whole new generation of powerhouse detectives are on the case. We've got the DESI survey, which is already dropping hints that dark energy might not be what we think it is. We've got the Euclid Space Telescope and the Rubin Observatory on the ground, and they are building the most detailed 3D maps of the universe ever made. These projects are literally designed to solve mysteries just like this one. So the case is very much still open. And the stakes, they honestly couldn't be higher. Solving the riddle of the dark flow could give us our first real glimpse into what came before the Big Bang, or even into other universes entirely. It leaves us with the ultimate cliffhanger. What really lies beyond the edge of everything we can see?